All right, welcome to exercise number 4. It's entitled the electromagnet, although I really should change it to a solenoid. Same thing, solenoid is an electromagnet. Now, this is actually a professionally made electromagnet, meaning, they do it in a more controlled conditions than what I did in exercise number 3. So they have a lot more loops on here. Let me show you how big it is. So it's a very long solenoid, and there's layers of wire. So the top layer that you see is not the only wire. It's layered. It has like 2 or 3 layers on there. Now, you may think that it's nice and shiny. It actually is bare metal. This is not bare metal. It's insulated. And if you actually look at the ends right here, you can see copper, that really bright copper part. That's with the red part scraped off. I scrape off the ends, and then we attach it to the screw to make nice electrical contact. And over here you can see the same thing. To see how the red goes up here, and all of a sudden you see the bright copper. So there's copper underneath there. It's copper wire, but it's painted with an insulator, so that there's no electrical connection within the wires. Each of those loops in there produces one magnetic field. And what happens if you have lots of loops, you have lots of magnetic fields pointing in the same direction, and you have a much stronger field. The more loops you have, the stronger the magnetic field. And of course, the stronger current you have also, you will produce a stronger magnetic field. So why don't we make an electromagnet? So this looks a lot more professional than what I did. So what I'm going to do is I've got the power supply. I'm going to take the red end and put it to the left for right now, just arbitrarily. We're going to switch it in a couple seconds after we look at what happens. And then I'm going to put the negative end to the right end. Now, it does say put a multimeter on there. It turns out that this particular power supply, it works pretty good. So we're going to use the multimeter on this power supply. It's already built in. And it says go set the voltage at 3 volts. So you can see that I got it at 3 volts, and that's the left thing. See the 3.0 and then the V, that's the volts. Notice to the right of it, it tells you how many amps is running through it. That is a lot of amps, way more than will kill a person. So I don't want to touch this. However, even if I did, I wouldn't get electrocuted because my hands are not wet. My hands have a really, really high resistance, so even though I touched it, the current will still go through the path of least resistance. There would be a tiny little current that goes through my hand, but virtually nothing. And almost all of it goes to this wire, which has like less than an ohm resistance. It's very, very low ohmage. So I guess there's some resistances due to the patch cords and the wires and stuff like that. So it's a lot of current, and this thing is going to get hot over time. But now, what we're going to do is see what happens, what type of magnetic field is produced by this. We already know it produces a magnetic field because it picked up some of these pins. When I made a simple one, it picked up some of these pins from the first exercise. So what I'm going to do is take a compass, and I'm going to put it near the left end where the positive current is going through. We're going to see. So when you look at a compass, that arrow, the red and the green arrow, that points, that's the north pole of that little compass needle. So the north pole of the compass needle is pointing to this end. So what does this end, what type of magnetic pole it is? Well, what pole attracts to the north pole? Is this a north pole or a south pole? Does the north pole attract a north pole, or does the north pole repel it? Does the south pole attract a north pole, or does the south pole repel it? So if this is the north pole of this little magnet that's sitting over here, and the north pole is going towards this end, so what type of pole must this be? Again, you can write that down in your table. Now what I'm going to do is move the compass over to the other side, and I'm going to move my iPad slightly so you can see what's going on. All right, so now you can see that the compass sort of turned around. Instead of the north pole facing, it's the south pole, that the end of the arrow is the south pole. So what attracts the south pole? Another one, this right end, what type of pole is this? So you can see they're opposite poles. In fact, it's quite similar to when we did the little, well, let's actually see because we didn't do it. I'm going to put a bar magnet right here. I'm going to do the same experiment with the bar magnet. I'm going to flip it up so you can see the poles. I've got a north pole here. So let's go look. All right, can you see I have my compass next to the bar magnet? So the compass needle, North Pole, South Pole. The South Pole is attracting to the North Pole. Now I'm going to move my compass needle over to the south, and the North Pole is attracting the South Pole, which it should. All right, so in other words, one end is the south and one end is the north. Can you see how the solenoid resembles that? And what you can do is kind of play around with the compass. You can watch as it moves sideways. You see how it moves sideways like this? And then it turns around like that. So watch the compass. What I'm going to do is sketch it underneath here. It looks like the field lines are going like this, out of one end and into another end. And since the North Pole is attracted to this end, this must be the South Pole, right? And this must be the north end. So that means the field lines, I'm just trying to figure out what the direction of the lines are. Okay, got that? This is really identical to what we see in a bar magnet. So now it asks you to disconnect the power and switch the leads. So that's what I'm going to do. So notice how now we have a South Pole at one end on the left end and a North Pole on the other. Flip off. Now I'm going to switch the leads. Black where the red was. Okay, so now I have the red. Flip it on. So now it's still at 3 volts. And now you can see my black and red leads has switched each other. So what I'm going to do is move my compass towards the left end. So now notice instead of the red end pointing this way, the tail end points towards that way. So this is the south end. So what do south poles attract? That would be that pole of the magnet. And then you can see as it moves by, it looks similar to my line, except for the fact that it's changed in its direction. So here the north end is pointing towards what? It's got to point towards the pole that attracts it, the South Pole. So notice how before the tail end was here, now the tip is here. You get the idea. What happens if you flip the current in a wire? You flip the poles. So that's the whole thing. So in a permanent magnet, you cannot do that. Let's look at a permanent magnet. Okay, let's try and flip the poles. You can't. You just can't flip the poles. It does not happen in a permanent magnet. You can't change the magnetic field at will. You can change a magnetic field at will using this device. All I have to do is move that voltage up, and the current will go up, and thus my magnetic field will get stronger. And watch what happens when I turn it off to the compass. Off, on. It's off, on. So an electromagnet can be, you can make magnetism however you want. You can make it strong, weak, off, on. Whereas a permanent magnet, you're kind of stuck with the amount of material you have and the strength of the field. You can't turn it off. I can't turn this field off. It's stuck forever. Although it will get weaker with time, and it may reverse directions if you actually put a very strong magnetic field against it. Again, this is iron, and it can actually, you can actually strengthen a little bit, but there's a maximum amount that a bar magnet can have, and then that's it. You can't turn it off. So there's definite advantages to electromagnets. The disadvantage is if you don't have any power, you don't have any magnets. So if you're out of power, then you're out of luck. You're not going to get any magnets. Okay, so I think that is exercise number 4, and that's pretty much it. Oh, I see. No, there's one more part with the iron bars. So I have this iron bar right here, and I want to see if it makes my magnet stronger. So what I'm going to do is turn the magnet on again. So I'm going to put this the compass, a little far apart. So first of all, let me actually get rid of this magnet. So it naturally points in the north direction. So it's pointing north right now, and I have the magnetic field off. If I turn it on, it moves 90 degrees. Okay, so what I want to do is have it move a little less than that so that I can see if there's an effect on the strength. Okay, so that's about what I'm going to do is actually move this around so that the north points this way, so it's a little easier. Turn it on. It's about 50-degree deviation. All right, so I'm going to, without changing the voltage, I'm going to put this metal bar inside of the solenoid, inside the solenoid, and we're going to see if it deviates more or less. Okay, now do you see how it went all the way further away? It went to 90 degrees. That indicates a stronger magnetic field, because the field will be parallel to the solenoid when it's really strong. I moved it further away, so it got a little weaker, try to point a little bit towards the north. Now I'm going to remove that big iron bar, and it'll get less strong. So again, it's in between the parallel of the solenoid and the north. It's kind of competing. This compass needle is attracted to the north pole of the Earth, but it's also being forced a little bit by the solenoid. So you can see when I put the iron bar in there, this needle flips really quickly. It's because the solenoid gets a lot more strength, and it's able actually to pull the compass to match the field lines, because the solenoid has field lines that are parallel to it outside of it. But if it's weak, then the north pole of the Earth is going to overwhelm it. Okay, so I'm going to turn this off, and you can see it goes back to north, and that's it for exercise number 4.